This is less of a 1 in 10,000 shot for me. Stefan Kaczmarczyk, very well known to everybody here, I hope. Yeah, I mean, Stefan does not need any introduction, so I won't waste any more time. Stefan, over to you. Thank you.
Thanks very much for having me. In this presentation, I will address the issue of dynamic loads in ropes. So in many ways, I think it ties a little bit with Tim's presentation, but a slightly different aspect. All right, so the background for this work is follows what I did over the last few years. I will look into how the dynamic loads in ropes are affected by dynamic phenomena, in particularly in high-rise buildings, and how this is affecting traction, because those are very closely related. So the outline is as follows. The introduction, I will show basic arrangements in high-rise lift, where most of you know. Look at the sway of the building and the conditions. Again, that's the theme which is important in high-rise buildings and needs to be assessed in many aspects. The results which I show are based on computer simulations, and I will present some results based on the case study. And then be summary and conclusions. Okay, so let's have a look here. This is a typical configuration of the lift in a high-rise building. So in high-rise building, we've got lift which has got a compensating system. So they are moving at speed, and the compensation is part of the picture. And the cable's ropes vary with time. So we have a car suspension at the top here at the moment. Car is at the top. Counterweight is the bottom. And we've got compensating cables at both sides, and obviously hoist ropes both sides. And also we have a compensating sheave assembly. So now the car moves down, and that's okay. What is happening during this time? The ropes change their length, the frequencies of the ropes are changing. And when there is a wind or seismic conditions, the building sways at low frequencies. And then when the frequencies coincide of the sway and of the ropes, and also of the masses, then we've got the issue with resonance conditions. So that's the main point in terms of dynamic situation which we have here. So adverse dynamic conditions. Okay, in terms of what we can experience in the design of lift, we do calculations and consider a range of parameters, including friction and traction. However, in most calculations we do, following the standard, we do not accommodate rope vibrations. What we do accommodate is rope acceleration and how this affects. So when we have a system which involves, this simulation doesn't go that way as I'm supposed to be. We've got vibration in the longitudinal direction, in the lateral direction, and there are two planes in the lateral directions. In plane, which is here, in out of plane. And what is important here, that then we have vibration of the car and vibration of the ropes. They are coupled. So that means they are not independent. They interact with each other. And we see how this can be accommodated. So again, we need to develop some basis for the analysis, and this is based on models. So the model of the lift here is sort of standard, but which has got car mass, which is moving up and down. The transport motion is prescribed by the control system. The traction is to be maintained during normal operation, car loading, and emergency braking. And we assess this using this formula. Everyone knows it. T1 over T2 is less than critical traction ratio. So T1 is the higher value, T2 is the lower value. And then when it is satisfied, we've got traction. In the model, we need to apply some simplifications. So in this case here, rope is bending over the sheath. This, in the analysis here, will be neglected. Now, we have a tension in the ropes. We need to assume again, for the simplicity, that the tension is equal in all ropes, which is not exactly the case, and Tim mentioned here. However, for the dynamic analysis, it is a valid assumption. Then we look at the deformation of the building structure, and this shown is the deformation is this red line here. And we take into account the fundamental mode of the building, which is typically for high-rise buildings within the range of 0.1 hertz to about probably 0.5 hertz. This can be approximated by some mathematical approximations. In that case, that's a polynomial, cubic polynomial function. However, in practice, we could do analysis using finite element method. You can get at the design stage of the building the shape of the fundamental modes of the buildings. Basically, it sways. So what then we take into account all the masses here, car, counterweight here at this stage, masses of the compensating sheath at the bottom, masses of the ropes, and how they move together. The system is complex, so all the interactions take place, and that's need to be accommodated in the model. The model is briefly sort of outlined in the paper, so I will not spend here much time to analyze it further. I will go straight to some fundamental parameters. That's a case study. So what we need to know in order to do the analysis, the calculations, is to consider the masses, and that all the masses are involved. Car, counterweight, compensating sheave ropes, and also anything else which is involved in the system. What is important here are the frequencies. So typically, as I mentioned, the sway frequency in the tall buildings over, say, 300 meters or about it, are within the range of 0.1, 0.2, 0.3 hertz. So in this here, we take the high-rise model of the building, and the frequencies of the structure of the building is assumed taken as an example within the range of 0.175 to 0.22 hertz. And those are different values for in-plane and out-of-plane. Building basically moves in the two directions. So overall, it moves in that way. So now when we've got, go back here, when we've got those frequencies, we map them on the frequencies of the ropes. And that's what is here in this picture shown. Okay. So the first picture shows the frequencies of the ropes, and they are hoist ropes for during at the counterweight side and at the car side. They change during the motion. So if the car is moving down, the frequencies of the hoist ropes of the car side are going down, and the frequencies of the counterweight side going up. The frequencies of the building here are horizontal lines. So that's 0.17, but about 0.2. That's a very typical situation for the hoist ropes, when we've got at the extreme points of the travel very close relationship. The worst situation is when we take compensating ropes. Compensating ropes are less tensioned, and therefore, here again, there are compensating ropes at both sides. We plot them here, we map them on these two red lines, and we see that the crossing lines, which are here above, okay, just here, okay, they are circled, and here we've got resonances. The most difficult situation is the mid-travel. Again, this is not an unusual situation. We all can't have this in the high-rise buildings. There is another set of frequencies we need to take into account to do the calculations. Those are frequencies of the vertical masses. Basically, they move up and down. on both sides. However, those frequencies here, if you look, there are several frequencies in the vertical direction. They are always above the frequencies of the host building structure. So you would think you don't need to be concerned about them, but actually there is interaction between the lateral motions of the ropes and the motions of the masses. Okay. So here is some results of simulation. The car is moving down, counterweight is moving up, and the top animation shows the motion of the hoist rope at the car side. The bottom animation shows the motion of the ropes at the compensating side of the car. Okay, they move. Car is moving down. Now when we look at the counterweight side, similar thing, but opposite. So when we have the hoist rope of the counterweight moving up and compensating rope at the counterweight is extension, is basically extending. So what is happening now? Those motions are coupled with the motions of the car and the counterweight. So the counterweight, the car, and also compensating shift are not keeping still. Here's the picture of what is happening with the vertical motions of the car and the counterweight. And also here, the bottom is the motion of the compensating shift. So the car, specifically from the beginning here of the mid-travel, starts to move quite a lot. Now we look at the counterweight moving, and the compensating shift is also moving. So what is here, there is no specific excitations in the vertical direction. It is the cables which are moving at a large amplitude, they're pulling up and down the vertical masses. And what we do now, we can calculate the tensions. So based on this, here are the tensions. So at the left-hand side, you have a tension in hoist ropes at the car side. Okay, I'm not here. And then at the counterweight side is the second set of curves. Now, when we now take those two, we can calculate traction, applied traction ratios. So what we see here, around this point, we've got quite large value of applied traction ratios. What does it mean? If we now take and we consider applying specific grooves into the traction sheaf, and let's say consider undercut U groove. If we look here, this value is about 2.52, so that's the instantaneous value. And we calculate, and we take some extreme values for the critical traction ratio with undercut U groove. That means gamma, the groove angle 25 degrees, like per standard, and the undercut 105 degrees. We arrive into friction value of 0.1417, and then when we take the minimum traction, critical traction value for the, say, single wrap, 160 degrees, and the double wrap, those values are less than the applied traction. So instantaneously, in that case, we would have a situation where the traction is lost. So traction is lost in this case. So that means that's our Euler formula looks like this. T1 over T2 is greater than critical traction value. What can be done? Okay. if we take now instead of undercut U-groove and we take V-groove, hardened V-groove, the situation is slightly different. So for the V-groove, we've got the critical value of tractions for the double wrap, which is now much better. Basically, in that case, you have a situation that traction is maintained. So the cost is here, but when we replace the groove, undercut U-groove, with hardened V-groove, is the lifetime of the rope. We know that V-grooves can reduce lifetime of the rope up to 90% few. So what next could be done? Obviously, the way would be to avoid the situation for the ropes not to be excited by the ropes, by the building structure. However, it is not possible using the means which very often designers have due to constraints. So, if we take into account implementing another component into the system, which is commonly used in high-rise systems, it's called tie-down. Hydraulic tie-down is attached at the bottom of the compensating sheath and to the pit, and this restricts motion of the compensating sheath assembly. Many options are here. Basically, the design of this element here is based on the force which is given by this formula, and depending on what we have at our disposal in terms of design, we can limit the motions of the vertical masses, and that is shown over here. So the red line is the previously calculated traction vertical displacements of the masses, and now the blue line is after we apply compensating sheath, tie down, and then the applied traction ratios are in blue line. We avoid these peaks here. So there's another option to take into account, and that's common again situations where we apply tie downs in the high-rise buildings. So, in the summary, in the standard calculations, rope vibrations are not considered in respect of traction. The dynamic conditions which arise in high-rise lift installations due to sway of tall buildings may affect the rope tensions, both in hoist and compensating system. This in turn might compromise traction. To make an estimate of applied traction during the sway conditions, we need to apply specific dynamic model. So, as we do standard calculations, we don't take into this account. We take into account only deceleration, acceleration. And then we apply the design of the final product. When we have the simulation results, we can choose what solutions could be applied. So that's, in a nutshell, I think I've done it in 15 minutes.
I see a question here, and I have a question, but I will tackle Stefan over a cup of tea. Yep. Do you have a microphone? Do you want to borrow this?
John Koshak from the U.S.
Hi.
Is there a special rule or rule of thumb with regard to how much mass and at what number of landings, how many floors before you start to consider?
It is individually for installation, depending on the building type. So typically, that has to be assessed on the case-by-case basis. And we start from, there needs to be base value. So when the design procedure starts, we start from the assumed number of ropes, masses of ropes, masses of car on the counterweight, and then there are two aspects need to be taken into account, whether the car is fully loaded or not loaded. That gives us a base. Then we do the calculations based on the specific model. And once we arrive into this frequency curves I showed earlier, then we say, you see what the conditions are. Now, there might be a case that you will be able to change the masses to move the resonance. So it is on the building. So depending on the height of the buildings are not symmetric. The frequencies are different in two directions. And this example, which was here, 0.17 hertz, 0.22 hertz, is a typical. There might be some extreme values as well.
Thank you. Please, and I'll see you out there for a cup of tea.